We are now ready to start into Unit 3, all about quadratics. So far, we have been spending all of our time talking about linear functions in Unit 2. But now we're going to shift gears because not all models in life of different scenarios can be modeled with a straight line. Think for a minute that if I were to throw a ball into the air, the ball would not just go in a straight line until it hits the moon. It would actually, because of gravity, go up for a while, and then eventually it would kind of start to come back down. So if this is time, and this is the height of the ball, you don't need to write this down just yet. I'm just giving you an intro of why we need quadratics. If I throw the ball from a height of 4 feet, the ball could go up for a while, and eventually it will come back down and hit the ground. Because we have scenarios like this in life, we can't just model everything with lines. We're going to need quadratics. Quadratics have a degree of 2. Notice this quadratic function right here is in standard form. There is a quadratic term, meaning a term that has the variable to the second power. There's a linear term, which means a term with just an x, and a constant term. A lot of times we call this particular graph a parabola. We call linear functions lines. We call quadratic functions parabolas. Let's go back to Unit 2 for just a minute. And again, this is not in your notes, so you don't need to try to figure out where this came from. I just want to go back and think about when we were graphing lines. The lines were in different forms. Sometimes they were in slope-intercept form, sometimes they were in point-slope form, and sometimes they were in standard form. We could change between the forms all the time. If we were in point-slope form, we could make that slope-intercept. If we were in slope-intercept, we could change it to standard. If we were in standard, we could change it back to slope-intercept. The same is going to be true with our quadratic functions as well. We're going to be able to use different forms for different situations, and we can change from one form to another. Remember, with lines, we began at -3, we moved the slope, we got our line. We could have also begun with a point, -4, -6, move the slope, we get a line. We could also use intercepts. When y is 0, x is 4. When x is 0, y is -3. Notice we get the same line each time. We're just starting with different information. The same is going to be true with our quadratics. We're going to have standard form that looks like this. That's going to be our standard form. And that's what we're going to focus on today primarily. There's also going to be a form called vertex form that looks like this, which we will get to a little bit later. And we also can use factored form, where we take the quadratic and factor it, which you probably remember doing back in Unit 1 earlier this year. I'm just going to use P and Q and call that factored. All right, so let's go back to our notes, the notes that are part of your guided notes, and start taking a look at some of these key features that will help us graph. If you recall, with these lines that we just graphed, 2 points was sufficient. We always got the same line if we had 2 points. With a parabola, that's not enough. We need more than 2 points to get the shape. Typically, 5 points is recommended. And not just any 5 points, because think if I have these 5 points right here, that's going to be very hard to tell where the parabola shape is going. I need to have maybe these 5 points so that I can then draw the proper curve. The main point that we are going to use is the vertex. It's right here. Every parabola is either going to open up or open down. The lowest point of a parabola that opens up is the vertex. The highest point of a parabola that opens down is also the vertex. It's also the intersection of the parabola and its line of symmetry. All parabolas are going to be symmetric. There's an invisible line that you can draw right down the middle of that parabola, and the points are the same distance away on either side of that line. The equation for the axis of symmetry is going to simply be the coefficient of the linear term, b, over twice the coefficient of the quadratic term, a, and we're going to take the opposite of it. That's going to give us our axis of symmetry. Another helpful point is the Y-intercept. And just like when we used intercepts with standard form, to find the Y-intercept, let's write this out. To find the Y-intercept, we make x 0 and solve. So if x is 0, this term is gone. If x is 0, this term is gone. B times 0 is 0. And c is what's left. So c is going to be the Y-intercept. That's a helpful point. That is the point 0, c. And then finally, when we know the axis of symmetry, we automatically get the x-coordinate of the vertex. The y-coordinate, we need to plug the x-coordinate back into the problem to figure out the y-coordinate. And it'll make more sense as we practice with actual examples. Let's try this first one. All right, I want to know where some nice points would be to graph this. So I'm going to have a t-table, x and y, with 5 points. But I want one of the points to be my vertex, which goes through the axis of symmetry. So this is A, this is B, this is C. Let's first find the vertex. And to do this, I'm going to do negative b over 2a, which would be negative 12, which makes it positive 12, over 2 times 3. And when I reduce this, 12 over 6, I get 2. So I know one point is 2. So I'm going to put it right in the middle. One x-coordinate is 2, I should say, more specifically. Now, if I want to know the value of y at 2, I'm just going to plug it in. 3 times x squared minus 12 times x plus 6. You can use your calculator to do this if you don't want to do the mental math, but it's not too bad of a point. So this gives me 12 minus 24 is negative 12, plus 6 is negative 6. So now I have my first point, 2, negative 6. I know this is also my axis of symmetry, so if it helps you, you can draw the axis of symmetry in, because you know the parabola is going to be symmetric around this red dashed line, which means I want to pick a couple points on the left side of my vertex, like maybe 0 and negative 1. And I want to pick some points on the right side as well. Maybe I'll pick 3, that's to the right, and I don't know, let's try 6. It doesn't really matter which points you pick. Sometimes they'll be nice points, sometimes they won't be integer coordinates. But we're going to just go back and substitute these values to get our y values. All right, so the first one I'm going to put a negative 1. Negative 1 squared is 1 times 3 makes 3. Plus 12 is 15. Plus 6 would be 21. That won't even fit on my graph. It doesn't go high enough. What if I substitute 0? Oh, by the way, that's a waste of our time because we know 0 pairs with C always. So right away I know it's 6. Next, we have 3. If I put a 3 in here, see what happens. That makes 27. Take away 36, which would be -9 plus 6 is -3. And then we'll try 6. 36 times 3 is 108. Minus 72 is 36 plus 6 gives me 42, another point that's not going to fit on my graph. But let's plot the ones that we can. 0, 6 is my y-intercept. That's helpful. 2, -6 we already have. That's our vertex. 3, -3 is right here. And then I have 2 points that I didn't choose very wisely. But guess what? When you're graphing parabolas, it's a buy one, get one free deal. If you know this point and you know it's symmetric, this point is one space away from the axis of symmetry. So if I go one space past that, I'm going to get a bonus point. I could have chosen that point. I could have chosen +1 and I would have gotten -3 when I plugged it in. Equally, this point right up here, buy one, get one free. It's 2 spaces to the left of the axis of symmetry. If I go 2 spaces further, I get another point on my parabola. And from here, you just need to connect your points as smoothly and nicely as possible. They go on forever, so we have arrows on the ends. The pretty skinny parabola. There we have it. So some key points: the vertex, the y-intercept, and the axis of symmetry helped us get a good graph. Let's go over to 1b. 1b isn't in standard form right now, so it's going to be very difficult to find the axis of symmetry and the vertex as it is right now because we don't know much about vertex form. Since we don't know that yet, let's go ahead and multiply this out. Right here, if I square x minus 1, I'd actually have to go off to the side, x minus 1, or use FOIL. Either way, we end up with 4 times x squared minus 2x plus 1 minus 3, which then becomes 4x squared minus 8x plus 4 minus 3 when I distribute. And then I can combine like terms to get 4x squared minus 8x plus 1. Now I can tell what A, B, and C are. I can now calculate the opposite of B over twice A. The opposite of B is 8 over 2 times 4, which is 8, which gives me 1. I know there's an axis of symmetry at 1. All right. I also know that if I put a 1 back into this equation or my original, it doesn't matter which one I use. If I put a 1 back in here, I have 1 take away 1, which is 0, squared is 0, times 4 is 0, minus 3. That gives me the point 1 minus 3. It would be right here. That's my vertex. Now I need some points on either side. I'm going to try 0. If I put a 0 in here, 0 minus 1 is -1, squared is 1, times 4 makes 4, take away 3 is 1, 0, 1. Buy one, get one free, I also know the point 2, 1 is on my graph. using symmetry. It's kind of a shortcut. Let's try -1. -1 take away 1 is -2. Squared makes 4. Multiplied by 4 is 16. Take away 3 is 13. So this gets high in a hurry. Be way up here. And buy one, get one free, we'd have a point up there as well. So now I can connect these. And there we go. Now, the nice thing is we could have skipped changing to standard form and started with our vertex form, because when it's in vertex form, when we have a coefficient, parentheses, with a binomial with x involved squared, subtracting a constant or adding a constant, that tells us where the vertex went from the parent function. Our parent function is f of x equals x squared. And when we graph that, it's a quadratic that looks like this, where 0, 0 is the vertex. This tells me that the vertex has gone 1 unit to the right and 3 units down. And sure enough, that's where the vertex landed. So that can be another way to find your vertex to start with without changing to standard form and using the -b over 2a formula. We'll talk more about transformations later on, I think around step 15 or 16. For now, you can just change this vertex form into standard form if that's easier.